I'm Samson. I'm one of the organizers of the workshop, and on behalf of all the organizers and staff, we'd like to welcome you to UCSD. It's great to see such wonderful participation in this EnCORE Workshop for Adversarial Robustness. Of course, this workshop is rooted in theory, and so it's great to see to hear from many perspectives in theory of complexity, learning theory, and cryptography. So, of course, this workshop is not about class. It's also about building collaborations and starting new conversations. So we do hope that you'll take the opportunity to learn, to connect, and grow. And personally, it'd be great if someone, a year or so would tell me down the road that this was a great experience. They met all these people and started, all these, found all these cool results in this workshop. So yeah, with that being said, so I just want to give a quick tutorial on adversarial robustness, highlight some of the themes of the workshop, and kind of foreshadow some of the talks that we'll be having throughout the next 3 days. Okay, so I know it's going to be boring for some of you, but hopefully others will get something out of it. And even for the experts in the room, maybe there's a thing or two that you'll hear. Okay, so yeah, so why adversarial robustness? Why should we have a whole workshop on this? Well, the most common example is that you have some complex environment. Maybe you have a network and you have a hacker. Okay? And so sometimes you have an actual adversary who's trying to cause harm. You can also think of this in terms of examples of adversarial ML. So many of you have seen this example where if you have a classifier, for example, and this thing on the left that will take in this image, I'll say panda, and then if you have some adversarial input that knows the internal models, the parameters of the model, then it could change these parameters by a small amount so that the difference in the pictures is imperceptible to the human eye, but then the classifier will say with high probability or high confidence that it's not a panda. Okay. So typically we'll want to say that adversarial input is one reason why we study adversarial robustness. But a much more, somewhat not as mentioned, application that is just important is in the setting of repeat interactions. So a lot of times, an honest user will interact with some mechanism, such as a search engine, for example, a database query, and the search engine itself will query some internal randomness, then it will produce an answer, and then based on its answer, you're going to produce the next query to the database. So one could say that your query is going to be not independent of the previous randomness that the database has considered. And so there are some adaptive interactions going on there. Of course, this could go also for stochastic optimization if you want to look at sample some random gradients, but use the same data structure over and over again to look at these gradients. Okay, so I'll go pretty fast over this. Just a quick warm-up example to motivate why adversarial robustness can break things. So this is an example from Omri in his paper in 2020, then Eliezer and Bev. And so let's say that we just want to do sampling. Okay? So we have some data sets. There are n items in this data set, and we want to sample something from this data set to make a representation of the data set for some definition of representative. All right, so maybe we want it to be uniform across the distribution, but what we can often do when the updates are one at a time, so you get n items one time, is you do reservoir sampling. So you might see one item, and you might want to replace your current sample with that item with some fixed probability. And this works. It's known that this will give you a uniform sample in the non-adaptive or standard oblivious setting. But in fact, we noticed that you can always make the random sample among the largest element of the set. And the attack is actually pretty intuitive, so let's go over this now. So an adversary will have a working range starting with the interval 0, 1. And then the first input to the data set would be 0.5. And so if you sample this data set, then the working range will be changed to the lower end, so it'll be changed to 0 and 0.5. But otherwise, if we do not sample it, then we'll change it to 0.5 and 1. And we'll always choose some element that is the midpoint of our working range, and that will be the next sample that we produce in the, sorry, that'll be the next item that's produced in the data set. So the main intuition here is that if we sample an item, then because we change the upper end of the interval to being the value of that sample, we'll always have the remaining updates in the stream be smaller than the sample that we took. So this is really not representative. We're going to sample something from a data set, but it's guaranteed that we'll always sample something from among the largest log n elements of the set. And in Omi's paper, he also noticed that this phenomenon applies to other approaches of sampling, like Bernoulli sampling and yeah. So again, the main upshot is that even fundamental primitives such as sampling are not robust. And so we need new techniques. But fortunately, due to many researchers in this room, there have been new connections that have been established across many areas. And sublinear algorithms is typical for the streaming model, but as far as I know, I was not previously aware of connections to differential privacy, adaptive data analysis, cryptography, and lattice theory, and many others. So we see elements of these connections throughout the course of the workshop. So more generally, the workshop themes are questions such as what attacks are possible against classical data structures and algorithms, and how efficient can we make them? And we'll have certain talks encapsulating this theme. We're going to ask what are the capabilities and limitations of robust data structures and algorithms in various models, and how do different adversarial models change what's possible? So I'll get to that question a little bit towards the end of this tutorial, but we also have a wonderful suite of talks there. And finally, we'll have a great set of talks on new problems and models of adversarial robustness.
Hey, Samson, quick question. Are these slides already available somewhere?
Maybe. So there's a Google Drive. Oh, I mean, like,
Yes, these slides that you're presenting right now.
oh, there's a Google Drive shared among the workshop participants. That yeah. So if I said anything that's inaccurate, please let me know.
No. This right here is extremely useful information.
Oh, okay.
But I won't need to probably ever.
Okay, great. Yeah, so that being said, if you want to provide a layer of redundancy for your laptop or not, we do have a shared Google Drive that feel free to put your slides there. Okay, so I'll only talk about the streaming model in this tutorial. I think it might give a good appetizer to the rest of the workshop. So in the standard streaming model, we have elements of an underlying data set, and these elements arrive sequentially. The goal, of course, is to evaluate or approximate some given function using space sublinear and the size of the input. And here the input could be either the entire data set, the universe size, or the length of the stream. So you might see a bit, and these bits are the zeros and ones, and your task might just be count the number of ones. Okay, so this is very simple. But more generally, we might have problems that are functions of a frequency vector, where a frequency vector is an underlying information that's defined by this data set, this data stream implicitly. So you'll have a stream of numbers, maybe they're IP addresses or whatnot from some given universe. And the ith element, okay, so first of all, let's assume that there are numbers from 1 through n. There's a mapping that we can do. And then the ith element in this vector is how many times I has appeared in the data stream. So the first element here is 5, and that's because you see 5 ones with data stream. Okay, so that's implicitly going to define a frequency vector. We don't have space to keep it, and that's the main challenge that we encounter in the streaming model. So what problems might you care about? Well, one problem that you might care about is the frequency moments problem, which is inherently also related to norm estimation. And the peak frequency moment is the sum of the peak powers of the coordinates in the vector. And this, in some sense, is one of the most fundamental or first algorithms that was presented for the area of streaming algorithms. And there's really beautiful work by Alon, Mathias, and Szegedy that shows that you get a 1 plus epsilon approximation to the second moment, F2, using just 1 over epsilon squared log n bits of communication. And the algorithm is so simple that I can't resist just telling you both the algorithm and analysis here. And so the algorithm is as follows. So let S be a random sign vector. So each coordinate of S is plus or minus 1 with probability half. And now let's assume that we have we can store S implicitly somehow, right? So we don't pay for actually storing S. Then what we want to do is just keep Z, which is the dot product of this random sign vector with our frequency vector. And this can be maintained implicitly and efficiently in a stream, because whenever you see an update to I, you can just add SI to your running sum for Z. So this is a quantity that we can maintain in the data stream, even if we don't get FI exactly. We'll get updates to FI, but we can do the corresponding transformation get Z. Okay, so that's Z, and if you look at Z squared, it's going to be this quantity right here on your screen. It's a bunch of cross products, but the main conclusion is that because they're random signs, SI are random signs, then when the indices are the same, SI, SJ is going to be 1. And so a lot of the terms are going to contribute to exactly the second moment. Right, so the cross terms when I are not equal J, we'll deal with that later. But when I equals J, that is that component of Z squared is exactly the second moment. Okay, then it turns out that when we look at the expectation, because again they're random signs, when we have cross products, each SI, Sj has expectation 0. You're taking the product of two random signs, so that's going to be 0. And so we can show that the second moment, show that the expected value of Z squared is exactly the F2. And the variance can do a similar calculation to show that's kind of small. Okay. And then we just need to use some concentration inequality to show that if we average 1 over epsilon squared instances, then we'll get 1 plus epsilon approximation with probably these two terms. Okay, so now that I've defined this algorithm, I'll refer back to it in a few slides, but keep this in mind as maybe a canonical algorithm that will show, for obvious reasons, fails when we have it adversarial. Okay. So that's one problem that is well studied. Another problem that's well studied is the related problem of heavy hitters, where you want to find the indices I such that Fi is at least an epsilon fraction of the overall norm. You could think of these as the maybe the scammers on some network, or the elephants for queries, iceberg queries. Another well-studied problem that we'll have various talks on and various attacks is distinct elements. And in this problem, we just want to estimate the number of distinct elements that appear in the data stream. So what's known about these algorithms is that for the non-adaptive setting, in the classical streaming model, there are results that can get 1 plus 1 over epsilon squared times some kind of sub-polynomial or logarithmic dependency for these algorithms. So the space accuracy trade-off is 1 over epsilon squared. Okay, so what is known about the adversarial setting? So just to lay the groundwork for the adversarial setting, the model is as follows. Each time, the input will be from some adversarial user, and the algorithm is required to produce some output. So let's say we're in the same problem as before, where you want to count the number of bits that are ones. And so the first input is a 1, and so our algorithm says 1. Then the next input is a 0, so there are still one number of ones in the stream. Then the adversary will see the output again, produce another bit, so on and so forth, until at some point, the adversary has compelled the honest algorithm to make a mistake. Okay, so it can be formally modeled as an interactive game, where at each time, the algorithm produces an honest output, and then the adversary uses the history of outputs to produce the next input, this game. Of course, the adversary's goal is to make the honest algorithm to mess up. All right. So in this case, it's clear that if we actually know the random sign vector, then the AMS algorithm will work. For example, if we just set the frequency vectors so that the signs line up with the random signs. So for example, if Fi is equal to 1 when the sign is positive, and if it's negative when the sign is negative, then the dot product is exactly the number of stream elements m. And so it's deterministic z squared is m squared, which is not necessarily, well, it's not the first one. So it's not the second one. And so what happened here is the randomness is not independent of the input, and that'll be a theme of issues, a recurring source of issues for various algorithms that people will discuss. Okay, so I don't want to mention this too much, but there's a more, so this was an informal attack where you kind of cheat and you know the signs already, but there are more formal attacks where even if you just interact with the output, you have no prior information about the internal parameters, and you can't produce some input that will compel the algorithm to fail. But I won't talk about this too much. Okay, so that looks bad, but one observation might be that in this previous attack, you need signs to line up. You need your frequency vector to have signs that line up with the random signs of the vector, sign vector. And so in this sense, deletions are needed to perform this attack. So a natural question is, of course, what can we say when the queries are insertion only, meaning that the frequency vector will only have non-negative coordinates. Okay, so this kind of was one of the results that kicked off the field. It's work by Ben Eliezer, J-Ram, Woodruff, and Negev introduced a suite of algorithms, multiple frameworks that show that we can get robustness in this setting. So the first one I'll talk about, it's also pretty simple and intuitive. It's called the sketch switching framework. And the main idea is as follows. Suppose we have some function that we're trying to approximate, and this function is monotonic, and the stream is insertion only, which means that the value of the function is only growing over time. Then what we can do is we can just run multiple instances of an algorithm, a streaming algorithm, and each time that one of these algorithms produces a value that's increased by 1 plus epsilon, can freeze this value and keep outputting this frozen value until the next algorithm produces something that is larger. Okay, so that was a mouthful. I think it's best illustrated with an example. Right. So here, let's say again that our goal is to get a 2 approximation for the number of ones in the stream. Same problem that we looked at before. And we have 4 instances of a streaming algorithm. Right. So these are the 4 that you see on your screen. And our goal is to get a 2 approximation. So as we feed in more inputs, then we will give those inputs to all of the streaming algorithms. And so after the first 2 updates, maybe all the algorithms say 1. Well, we've frozen the first one, and so we will keep outputting 1 until the next algorithm, the yellow algorithm, changes its input by a factor of 2. Okay. So maybe we see another update, and at this point, we've frozen the first algorithm, so it will always say 1 from now on. But the next algorithm produces 2, and so it's a factor of 2 apart. And so we'll switch over, we'll freeze the output of the second algorithm from now on. And we're always going to use that as the output. And then we'll keep going and update the latter algorithms. So we'll see another update. See 3. But we still don't reveal the randomness of the other algorithms. So on and so forth. So now when we see 4, again, we'll freeze the third algorithm, and we'll keep using that output until the last algorithm outputs 8. Okay. So the key is that at any time, the true answer is sandwiched between your frozen value and the value of your next algorithm that hasn't been output yet. And we're saying that the next algorithm will be frozen when its value is 1 plus epsilon more than the frozen value, and so your value, because your function is monotonic, is sandwiched between the frozen value and some value that's 1 plus epsilon more than the frozen value. And so it's going to be a good approximation. Very elegant observation. Okay, so that's the sketch switching summary. And the main idea is that you pay each time the value increases by 1 plus epsilon. So since previous examples I said have a 1 over epsilon squared trade-off between the accuracy and the space, then this will give you a 1 over epsilon cubed dependency overall. Okay. So another framework that was introduced by the same paper was computation paths. And I think this one hasn't got as much attention initially, but recent work has shown that this is a very valuable tool. So the main idea here is that we sort the upper bound, the total number of possible inputs, and just do a simple union bound over these possible inputs. And so for data streams, one can say that the number of possible inputs, okay, so first of all, let's say it's deterministic. And then your input will only change when you see some different output from the algorithm, right? So the algorithm is going to tell you one, it's going to tell you one, it's going to tell you one again, and suppose it's change over to 1 plus epsilon. So let's say the algorithm can only change its output by L times. Then the adversary can only see n choose L different times where the input has changed by 1 plus epsilon. Right? The output has changed by 1 plus epsilon. And so there are roughly n choose L different inputs that the adversary can generate. So as long as you have your failure probability be smaller than 1 over n choose L, then you're good. And if your space overhead for non-robust algorithms is log 1 over delta, then this means you get a L log m overhead for robust algorithms. But if you have a dependency for log 1 over delta, for example, quantile estimation has these dependencies, then you get a much better overhead. Okay. So I think this requires more information, but in the interest of time, I'll skip this. See that. Okay. So yeah, again, in interest of time, I'll skip some of this motivation, but I'll just say that this beautiful work by Stemmer and co-authors, I think Kaplan has done, Mansour Matthias, showed that there are connections to differential privacy, and these get better losses than initial works. And the main intuition here is that use differential privacy to hide the internal randomness of the algorithm. Okay. So the adversary is trying to learn the internal randomness to exploit and use differential privacy to hide its randomness. Also say that that's differential privacy work by Guy showed that in a different setting for adaptive data analysis, you can get somewhat the same qualitative results by subsampling instead of differential privacy. So one natural question might be to ask whether we can get similar results for subsampling in this model. Okay, finally, I want to mention that we were able to get type bounds afterwards using a notion called difference estimators. And the main intention there is that before we paid 1 plus epsilon, each time the algorithm increased by 1 plus epsilon, we paid for that. And so there's a 1 over epsilon overhead. But if the algorithm increases by such a small amount, right? If it only increases by 1 plus epsilon, maybe we don't need a fresh calculation for this algorithm. We don't need to spend 1 over epsilon squared space. Maybe we can get by with kind of a coarse approximation to how the algorithm has increased. Just see that, but that's just want to mention that for these problems we were able to get type bounds, but it's really just the tip of the iceberg. Okay, and let's get this as well. So you might ask, besides these problems, what other things do we know about streaming algorithms and robustness? And so I want to mention various notions of robustness for sampling. So like I said before, the paper by Ben, Eliezer, and Yogev showed that gave attacks on sampling, but at the same time they showed robustness for methods just for Bernoulli sampling and robust sampling. There's some follow-up work that showed important sampling is robust with various overheads by co-authors in this room, Barberman, Stem, Matthias, Shane. So I think big ways there. And in fact, these approaches showed that sampling algorithms are robust to what's known as white box adversaries. So skip ahead to white box adversaries. In these settings, this is the most powerful adversaries where before we said that the adversary has access to the output of the algorithm, but now the adversary will have access to the entire state of the internal state of the algorithm, including the internal parameters. And this more accurately captures some of the attacks for machine learning models that we saw in the first few slides. So one might ask what can be done there. Well, unfortunately, there are some reductions to deterministic communication complexities protocols that show that basically no non-trivial algorithms can be done for essential problems that we discussed earlier. But there is a positive result that says that if we assume that the adversary is bounded in some computational manner, for example, the runtime is at most computationally bounded, then we can use cryptography to get non-trivial algorithms against these white box adversaries. Okay, so that's one separation. Another set of separation you might ask is, well, what about when we only have insertion only when the adversary, again, only has access to the output of the algorithm. And there are some initial separations shown by Kaplan, Munzer, and Stemmer for the streaming adaptive data analysis problem. Again, we'll talk more about adaptive data analysis throughout this workshop. And finally, work by Chakrabarty, Ghosh, and Stokel showed a separation for the column of graphical. Okay, so that's kind of a preview of some things that were done. There have been many other beautiful works, attacks on classic data structures and algorithms, adapting classic, for both sides, right, attacks and defenses. But some good things to think about over the course of the next 3 days are the capabilities and limitations for insertion deletion streams. Refining adversarial models and actions. For example, if your adversary, whether it's white box or black box, has various restrictions, such as bounded time, space, delayed observations, some partial access to randomness, so on and so forth, or adversarial inputs in new problems and models, for example, NPC or discrete quantity. So again, I want to welcome you all to this workshop. Thank you for attending, and any questions before we hand things over to our first research talk. Yes.
Yes, I do. Well, thank you. I think this is very interesting. But I mean, like, so like, this is new to me, right? Like, I never worked on literature. So, just like, I'm gonna ask like very basic question.
I could do or we like work on the whole workshop.
Like, can you give me like a real world example of when you would have like a sort of algorithm that like try to estimate like your number of occurrences of things, or why would it be useful to have like something robust here? Like what would be like a scenario, like in the real world where you would use this thing?
Yeah, well, I can tell you some examples where people have made mistakes before, for example, in convex optimization, where they have these data structures that are sketches of the overall data set. And then they use that data set to find some gradient. And then this will give them an iterate towards an optimizer for some solution. But then once they have some iterate, then they'll query that data structure again, and maybe there are some dependencies between the current iterate and the data structure, and so you don't actually get an optimizer. Yeah, so that's a mistake. Or sorry, so that's an example where people have actually had issues before in research. But are you asking for more practical implications or practical?
Yeah, more like practical for people. So what I imagine is like you have like an adversary because like someone is trying to do something negative.
Right.
To you, right? Like, so how would you? So it's like, for example, you talk like about optimization.
Right.
Like, I start thinking, well, I mean, why would anyone get my computer and change what I know? Like, that's what I'm thinking about, right? Like,
yeah. So I think we're quite far away, but I think the area of adversarial machine learning has shown a lot of issues, and that's why machine learning algorithms can't be deployed in a lot of situations. And again, our work here is still quite far away from resolving adversarial machine learning, but the classifier example I gave at the beginning is an example of an adversarial attack, right? And so this will prevent things like military operations or even crucial devices from implementing these models.
yeah, and so it looks like the connection, so here we're talking like about ones and zeros and counting things, but it's like what I'm more familiar with is like the example of the panda when you change like your classifier. That like I can understand it, it's like
Yeah. So there are definitely examples of much more complicated problems. Clustering, regression, low approximation, and more data science problems. I think I just want to give some simple examples of problems that would be a bit more intuitive. But there are certainly many interesting, complicated problems that are not robust.
Okay, so maybe our final question. Sorry for all this, like I know it's like stupid question, right? But I really want to understand, So like, would it be like trivial to like sort of like take those ideas and adapt that to like more complex scenarios, like when you have like for example, like an image classifier, like is it like trivial to take these ideas that you just explained now And, you know, put them like in more, you know, complex.
No, I would say it's far from trivial, right? But I think, the goal of this whole direction, I don't know about what others think, is to build an algorithmic toolbox to start getting towards techniques for these more ambitious goals.
Great. That's all I wanted to know. Thank you very much. Great talk, really. I really listened.
Not me, I have some. Yeah.
So, the last slide, we talked about white box theory.
Yeah.
You assume the curve can favor internal state, does it also say like some randomness to use or no?
For the lower bound or the upper bound.
I mean, the model there. Does it say that your internal, does it also say, for example, if you're running like, does it?
Yeah. Okay, sorry. So, good question. Yeah. So, the model is saying that it has access to all internal parameters. It has access to all internal randomness that was previously used, but it won't have access to future randomness. For example, if you're going to flip coins, maybe you have access to public randomness that you can flip coins to sample in the future. So that's why sampling algorithms are okay to some extent, but yeah.
Nice.
Thank you.